Hey, what's up, YouTube fans? I wanted to read some of a paper here from the National Library of Medicine, which I found to be very interesting. They offered a solution to some of the biggest questions in regards to the origin of life, right? And they incorporate some concepts I've talked about before, like the anthropic principle. And it's of course highly speculative, but that's really all you can expect with something like this. But in any event, so the title of it is the emergence of life in an inflationary universe. This was posted February of 2020. Um, the abstract says abiotic emergence of ordered information stored in the form of RNA is an important unresolved problem concerning the origin of life. A polymer longer than 40 to 100 nucleotides is necessary to expect a self-replicating activity, but the formation of such a long polymer having a correct nucleotide sequence by random reactions seems statistically unlikely. However, our universe created by a single inflation event likely includes more than 10 to the power of 100 sun-like stars. If life can emerge at least once in such a large volume, it is not in contradiction with our observations of life on Earth, even if the expected number of abiogenesis events is negligibly small within the observable universe that contains only 10 to the power of 22 stars. Here, a quantitative relation is derived between the minimum RNA length required to be the first biological polymer and the universe size necessary to expect the formation of such a long and active RNA by randomly adding monomers. It is then shown that an active RNA can indeed be produced somewhere in an inflammatory universe, giving a solution to the abiotic polymerization problem. On the other hand, it has a mathematical term here, must be shorter than 20 nucleotides for the abiogenesis probability close to unity on a terrestrial planet, but a self-replicating activity is not expected for such a short RNA. Therefore, if extraterrestrial organisms of a different origin from those on Earth are discovered in the future, it would imply an unknown mechanism at work to polymerize nucleotides much faster than random statistical processes. Introduction. In spite of recent rapid development of biology, chemistry, earth science, and astronomy, the origin of life, abiogenesis, is still a great mystery in science. A prominent feature of life is the ordered information stored in DNA and RNA, and how such information appeared from abiotic processes is a crucial issue. The RNA world hypothesis postulates an early era when RNA played both the genetic and catalytic roles before the DNA protein world came into being. This is widely accepted due to strong supporting evidence, including catalytic activities of RNA, especially its central role in a ribosome. However, a more fundamental and unresolved problem is how an RNA polymer long enough to have self-replicating RNA polymerase activity, i.e. RNA replicase ribosome, emerged from prebiotic conditions and then triggered Darwinian evolution. A key quantity is the minimum RNA length required to show a self-replicating ability. RNA molecules shorter than 25 nucleotides do not show a specified function, but there is a reasonable hope to find a functional replicase ribosome longer than 40 to 60 nucleotides. RNA polymerase ribosomes produced by in vitro experiments so far have a length longer than 100 nucleotides. Furthermore, formation of just a single long strand may not be sufficient to initiate an abiogenesis event. Instead, a pair of identical strands may be necessary if one serves as a replicase ribosome and the other as a template. Polymerization of RNA in water is a thermodynamically upheld process, and hence reacting monomers need to be activated. Non-enzymatic reactions of adding activated monomers, e.g., imidazole activated ribonucleotides to an RNA oligomer, have been experimentally studied. Reactions at inorganic catalytic sites, e.g., surface of minerals such as morillanite clay, may be partially efficient. It says particularly efficient. Some experiments yielded production of up to 40 mers of RNA, which may be long enough to have some biological activities. However, these results have not been reproducible, and only short oligomers of up to 10 mers were produced conclusively in recent experiments, with the abundance rapidly decreasing with the oligomer length. This trend is also consistent with the theoretical expectation for random adding of monomers. An experimental difficulty is that aggregates may easily be mistaken for polymers depending on detection methods. It is theoretically speculated that terminal ligation of oligomers may hierarchically produce further longer polymers, but there is no experimental or quantitative demonstration of this starting from realistic prebiotic conditions. A report of experimental production of long polymers, more than 120 nucleotides by ligation, has been subject to reproducibility and the aggregate polymer discrimination problem. A high concentration of oligomers is necessary for ligation to work efficiently, but this may be difficult because oligomer abundance rapidly decreases with oligomer length in polymerization by monomers, even if such a ligase activity exists. If we consider only the conservative abiotic polymerization, i.e., statistically adding monomers, the probability of abiogenesis may be extremely low on a terrestrial planet. This case is not in contradiction with our existence on Earth, because we would find ourselves on a planet where abiogenesis happened. The life on Earth is believed to have descended from the single last universal common ancestor, with no evidence for multiple abiogenesis events, and we do not know any life of a different origin in the universe. The emergence of life early in the history of Earth is often used to argue for a high abiogenesis rate, but an arbitrarily low rate cannot be robustly excluded because the chance probability is not negligible, assuming a constant abiogenesis rate where it has mathematical terminology, is the time of abiogenesis elapsed from the birth of Earth, and more mathematical symbols, the present age of Earth. it may well be possible that early Earth was a more favorable environment for abiogenesis than present. There may also be an anthropic selection effect favoring earlier abiogenesis on Earth because an intelligent life must emerge before the increasing solar luminosity causes an end of Earth's habitable state, estimated to be it has mathematical terminology there. For the case of a low abiogenesis rate, the number of abiogenesis events is often considered in the Milky Way galaxy containing about 10 to the power of 11 sun-like stars, or in the whole observable universe containing 10 to the power of 22 stars inside a spherical volume with a conmoving radius of 46.3 GLY. However, the size of the observable universe is not related at all to its whole physical size. According to the widely accepted view of the inflationary cosmology, the physical size of the universe created by an inflation event should be much larger, likely including more than 10 to the power of 100 stars. In that case, even if the expected number of abiogenesis events is much less than unity in a volume size of the observable universe, it may still be consistent with our observations, provided that abiogenesis is expected to occur somewhere in an inflationary universe. The aim of this work is to examine this possibility quantitatively, assuming that the first biological RNA polymer was produced by randomly adding monomers. Conan considered implications of the eternal inflation theory for the origin of life. In this scenario, most part of the universe inflates forever, self-reproducing many regions that undergo a conventional inflation followed by a hot Big Bang universe. Then an infinite number of stars and galaxies will be formed, and we expect emergence of life even if the abiogenesis probability is infinitely small. Though eternal inflation is a theoretically likely scenario, it is difficult to confirm observationally, and a quantitative discussion is impossible. It is then interesting to ask if life can emerge within the homogeneous region in which we exist, assuming its minimal size necessary to explain observations. This work tries to give a quantitative answer to this question. Then we have a section titled "The Size of the Universe Created by an Inflation Event." The observable universe is highly homogeneous and spatially flat on scales many orders of magnitude larger than the causally connected scale horizon in the early universe, which are called the horizon and flatness problems and cannot be explained by the standard Big Bang cosmology. Cosmic inflation is currently the only widely accepted solution to these problems, and furthermore, it naturally generates scale invariant quantum density fluctuations that serve as the seed of galaxy formation and the large-scale structure in the present universe. Its prediction is in quantitative agreement with the observations of the cosmic microwave background radiation anisotropy already constraining some theoretical models. There are many models and scenarios about how inflation occurred in the early universe, but all of them consider an epoch of exponential expansion where, and then it starts to go into mathematical terminology. So now we have a section titled Posian RNA polymerization. Here we consider a cycle of RNA polymerization by randomly adding activated monomers to an oligomer as a Posian process. Taking an experiment on clay surfaces as a model case, non-RNA nucleic acid analogs may have carried genetic information before the RNA world emerged, but the formulations below can be applied to such cases. And then we have a lot of math. So let's see, I'm going to scroll through some of that. In RNA oligomerization on clay surfaces, the coefficient K should be proportional to the concentration of active monomers absorbed on the clay surface. This clay monomer concentration increases with that in aqueous phase, but according to the Lagmoyer adsorption isotherm, it saturates when the absorbed monomer abundance reaches that of the exchangeable cations on clay surface. In the experiment, Montreal molite has 0.8 mmol exchangeable cations per gram, and it starts to saturate at an aqueous monomer concentration of it has mathematical terms here. So a lot of math. I'm going to scroll through some of that. A lot of mathematical jargon. Let's see. So now we have, it says, however, if we request one abiogenesis event somewhere in the whole physical volume created by an inflation, the chance of abiogenesis greatly increases. In a volume created by twice, 3, and 4 times as long inflation as that required to create the observable universe, it has an equation here, becomes 66, 97, and 127 respectively. These lengths now allow us to expect a self-replicating activity of an RNA molecule. If an identical pair of RNA strands is required for abiogenesis, it has a symbol here, should be effectively twice as large as each of the identical strands. Then an inflationary universe can produce a pair with a length of 33 to 64 nucleotides for each, and we can still expect replicase activity. It is also possible that the inflation duration is even longer than the examples considered here. Then a lot more mathematical terminology. Going to scroll down through all of that. And so now the conclusions. It has been shown that the first RNA polymer with a replicase activity can be abiotically assembled by the most conservative polymerization process, i.e. random Pausium adding of monomers. If we require that it occurs more than once somewhere in the physical volume of a universe created by an inflation rather than inside the observable universe for us. This gives a simple solution to the abiotic polymerization problem to initiate the RNA world. Equation 7 relates two quantities on vastly different scales. This reminds us of an Ouroboros. The result of this work may also give an explanation for the homochirality of life. Even if activated monomers supplied to the polymerization cycle are a racemic mixture, life emerging from them will be homochiral if homochirality is a necessary requirement for an RNA polymer to show biological activities. Simply, it needs to be it needs more time or volume for a homochiral polymer to be assembled by random polymerization with a mathematical term here, twice as large as when ignoring chirality. As shown in figure 1, Change of that same mathematical term by a factor of 2 does not seriously affect the expected number of abiogenesis events in an inflationary universe. On the other hand, the expected number of abiogenesis events is much smaller than unity when we observe a star, a galaxy, or even the whole observable universe. This gives an explanation to the Fermi's paradox. The observable universe is just a tiny part whose volume is likely smaller than 1 in 10 to the power of 78 of the whole universe created by an inflation, and there is no strong reason to expect more than one abiogenesis event in such a small region. Even if Earth is the only planet that harbors life inside the observable universe, it does not contradict the Copernican principle because life would have emerged on countless planets in the whole inflationary universe in which we exist. In the picture presented here, the probability of finding biosignatures from planets or satellites in the solar system or from exoplanets is negligibly small, unless we consider the interplanetary or interstellar travel of microorganisms, and there's a few footnotes on that. It should be noted, however, that the case of a high abiogenesis rate cannot be excluded by this work because we assumed that abiotic RNA polymerization occurs only by the random Pauzian process of adding monomers. Potential roles of much more efficient processes on the origin of life, such as nonlinear auto or cross-catalytic reactions, have been studied theoretically, though it is highly uncertain whether such processes really worked in realistic prebiotic conditions. If organisms having a different origin from those on Earth are found in the future, it would suggest that such a mechanism is working at abiogenesis to reduce, it has a mathematical term here. Although this possibility should not be excluded, what is shown by this work is that such a hypothetical process is not necessary if we request abiogenesis events to occur somewhere in an inflationary universe. It is also worth pointing out that in the, it has mathematical terminology here, relation for, there's a lot more math here, so let's see, I'm going to scroll through some of the math. Okay, a fundamental assumption in this work is that an abiotically assembled RNA polymer acquires a self-replicating ability if it is sufficiently long and has a correct nucleotide sequence. This may be rather trivial under the physical laws ruling this universe, because we know that ribozymes are actually working in life and can also be produced in vitro experiments. This work considered only a single homogeneous region in the universe created by an inflation event, obeying the same physical laws that we observe. However, the multiverse hypothesis implies existence of other universes created by different inflation events in which physical laws may be different from ours. A theoretically intriguing question is whether a chemical RNA-like long polymer is easily formed to contain information and show biological activities, eventually leading to higher organisms, when physical laws are arbitrarily made, e.g., random choices of fundamental physical constants. Perhaps this may be the ultimate mystery regarding the origin of life, which is, of course, far beyond the scope of this work. So, that was a very interesting paper here. I like the incorporation of anthropic principle thinking and explaining statistical improbabilities by chance and the anthropic principle and by certain models of the universe, right? That's what I like about this paper. It offered a solution to some problems in regards to the origin of life. All right. I hope you guys enjoyed. That's all for now. See you guys.